Welcome back to 2024. We are going to look at the first algorithm for solving convex MINLOs. So remember that convex MINLO is sort of a misnomer because the problem itself is non-convex because of the presence of integer variables y. Okay. But the fact that G's can be convex greatly simplifies the search for optimality because of these nice properties of convex functions. Okay, so we are going to assume that the functions f and g are convex as well as twice continuously differentiable. Convex because we would like to use some underestimators or these linearizations, and twice continuously differentiable because occasionally in our algorithm we would like to solve some restriction of this problem by using some nonlinear optimization method which uses KKT conditions, which relies on first order derivatives and also sometimes second order derivatives to check for whether a given point is minimum or not. Okay, so both these conditions are important. We would like especially the y variables to be bounded because technically that can create some difficulties. And this is not a very big assumption because most of the practical problems, the integer variables are bounded. Okay, 99% of the time when we look at any integer problem, it has binary variables. Okay, so most practical decisions are 0, 1, on or off, left or right, yes or no. But in theory, if you are worried about why, and why if it is unbounded, then there is some difficulty in proving some results. Okay, so the motivation for this algorithm is called outer approximation algorithm. Okay, so practically speaking, even if you have a nonlinear optimization model, it is very likely that many of the constraints in your model are linear. Okay, for example, in the lab we saw that there were linear constraints which said that all demands have to be met and other things. Okay, that one out of these k items must be selected and so on and so forth. Okay, and also the fact that mixed integer linear optimization solvers are quite good. Okay, MILO in the worst case takes exponential time, it is NP hard, and in theory these solvers can take a very long time, and you can write models which take a very long time, but in practice for moderately sized problems with few integers, these solvers tend to be really good. And if we go back to the triple L theorem, Lutke-Lindroth and Leyffer theorem, and look at that table of how big an MILO can you solve, then Sven is a confident in betting $50 that some an MILO with 10,000 variables can be solved reasonably fast. Okay, so that is useful. Okay, so MILO is going to be a big component of this algorithm. Also, NLO solvers are quite good, especially when you have convex. All functions in your constraints are convex, and they are of moderate size. Okay, so using these two very big components, we can stitch them together and have a nice easy algorithm which is very easy to implement, but understanding why it is finitely converging or takes only a few iterations, that is a little bit involved. Okay, So we'll go slowly over it and try to understand why it works. Okay. So as I said, this algorithm is called outer approximation for convex MINLOs, first proposed by Duran and Grossman in 1986, and they showed that it works quite well for several chemical engineering type of problems. And later Fletcher and Leyffer analyzed it and showed some good properties of this algorithm. Good points about this method are you only need to solve a finite number of MILOs and a finite number of NLOs. It is not that it will converge only in the limit or something. Okay, so somewhat similar to simplex method that it converges in finite number of steps, and it is quite fast in practice. Maybe not the fastest of all algorithms, but still quite fast. And the best part is, in my opinion, that it is really simple to implement. Okay. All right, let's start. Okay, so I'll start with some intuition and try to build this algorithm from sort of first principles and start with some very simple ideas. Tell you why that may not be a good idea, and then refine those ideas as we go along. Okay, so suppose you didn't have an NLO solver and you still had a MINLO problem to solve, and for sake of simplicity we can assume that all the y variables are binary. So all y variables will either take value 0 or 1, and suppose you only have an NLO solver, nothing else. Okay, so I'm sorry, I earlier said you don't have, but suppose you only have NLO solver, nothing else. It's a very nice island to be on. You are stuck on an island and you only have filter SQP or IPOP with you, and you want to solve this MINLP. So the most obvious idea is to do what? You can solve a relaxation, okay, and then do what? That's a little bit complicated. I'm asking for the simplest possible thing. So the simplest possible thing that I could think of was to try all possible combinations of y. Okay, so you fix y first to all y's to 0, then solve whatever you are left with, and that could be one possible solution, and check if it is feasible or not. Okay, and then set one of the y's to 1, then some other y to 1, and try all possible 2 to the power p combinations. And obviously this will take too long a time. So the obvious question is, can we avoid choosing such poor values of y from this set? Okay, and if you think about it a little bit, these mixed integer linear optimization solvers do exactly that. Okay, given y variables of this type, and when you ask MILO solver to find an optimal solution, it prunes out a lot of these values based on linear constraints and never visits them, and tries to find the answer in as few trials as possible. Okay, so that is what we will use here also. So instead of trying all possible values, we will ask an MILO solver to tell us what are good values of y to choose. Okay, and remember, this is a good idea because I told you that most of the constraints in these problems tend to be linear. Okay, so an MILO solver can look at those linear constraints and eliminate a lot of useless y's. Okay, so here is how we can start. Okay, since our objective function is also nonlinear, we will use the standard trick that Sven mentioned and bring it down as a constraint. So this is my original problem, and I'm going to write it like this, and I'm going to change the notation slightly more to highlight the fact that there are some constraints which are nonlinear and there are some constraints which are linear. So I'm going to separate them out. Okay. And at the first step, I'm going to just remove all the nonlinear constraints from my model. Okay. So then I am left with only linear constraints and integer constraints. Okay. What is H? So this is part of some linear constraints. Okay. So earlier we said that our constraints are of the form gxy less than equal to 0, but some of those g constraints will have only linear things. Okay. So I have separated out g into two parts. So the g in the right hand side model has only nonlinear constraints, and all those things which were linear inside g, I have written them explicitly separately. Okay. So in the right hand side, those g plus those constraints is same as the g here. Okay. Make sense? All right. So I am going to start with this model, and as the first step, I am going to remove all the nonlinear constraints. Okay. And then I will be left with an MILO. Okay. And I am going to solve it. Okay. And this question everybody should be able to answer, that if I get an optimal objective value from my MILO model, it will be a lower bound to my original problem. Why? Because it's a relaxation. I have removed some constraints from my model. So whatever solution I get from my whatever is the solution of the MINLO is also a feasible point to this MILO, and that is why it's a relaxation. Okay. And the corollary is that if this MILO happens to be infeasible, then the original model is also infeasible. Okay. So then we can stop. Okay. If by chance I'm lucky and the solution x star y star of MILO satisfies all the nonlinear constraints also, okay, then also I can stop, because this would be the optimal solution of MINLO. Okay. So this is being plain lucky, okay, by chance. All right. Most of the time, there could be this. So for now, assume objective function is linear. Okay, we will come to that part also. Okay, it still works. Okay, but for now, just assume objective function is linear. Okay. If the MILO is unbounded, then we are sort of in trouble, because then we can't make we can't make a conclusion about MINLO. The MINLO might still be infeasible, or it might be unbounded, or in some weird cases it might actually have a finite optimal solution as well. Okay. So this part we will leave out, because in the first slide we assumed that my variables x and y, they are both bounded. Okay. So under those assumptions, this case is not going to happen. All right. So we are left with the most common case is that the solution of MILO will violate some of the nonlinear constraints, because I had omitted them. Okay. But the good part is that the solution of MILO will satisfy the integer requirements on y, okay, because I just solved it using some integer solver, all right. So now the question is, how do I go to a different solution which might actually be feasible to the nonlinear constraints also, okay, and the answer lies in these linearization inequalities, okay. Any questions? Okay, so this is where the convexity comes into picture. So suppose the first nonlinear constraint is violated. So violated means that if I evaluate the function g1 at x star y star, then it is greater than 0, whereas we want it to be less than equal to 0. Okay, so the simplest I can try to do at this stage is to just add the linearization inequality at this very point. Okay, so let me draw a picture. So ideally, I want to be inside this feasible region, but the solution from MILO gives me a point here. Okay. So my first thought is to just add a linearization inequality based on gradients evaluated at x star and y star. Okay. First of all, we claim that it is a valid inequality. Why is it a valid inequality? Because G1 is a convex function, and this part underestimates the convex function. Okay, so remember, this is the linearization of a convex function at point x star y star, and for a one-dimensional function, we had drawn this picture that here if we have function g, and here if we have x, and we have a function, the linearization always lies below the actual function. Okay, so if an underestimator is less than equal to 0, so that means the original function is also less than equal to 0. Okay, so this is a valid inequality for my MINLO. Okay, any questions till now? Okay, and the second point is that if I put x star y star in this, I will see that it actually cuts off the point x star y star. Okay, look at these two things. We already assume that G1 is more than 0 at this point, and if I put x star y star in this expression, I get G1 x star y star less than equal to 0. Okay, so some contradiction, which means that this x star y star is not satisfying this inequality. Okay, all right. So in my picture, if I add this linearization inequality, I'll get a constraint like this. Okay, so this is this linearization constraint. All right. Any questions? Okay, this is a sort of a important idea in this discussion. All right. So that means I have been able to successfully chop off this point x star y star. So then I have an algorithm based on these two ideas of using MILO and generating these linearizations. Okay. So so what I can do, I can solve an MILO, check the solution x star y star for feasibility. If all constraints are satisfied, I am done. If not, then I will find which nonlinear constraints are violated, add this linearization, then I get a new mixed integer linear optimization problem with few more constraints, and then I solve it again. Okay. So this is like a cutting plane method for regular integer linear programs. Okay. And this has been proposed earlier by 3 or 4 studies involving Westerlund, and it is called the extended cutting plane method. Okay, so this method doesn't involve solving any nonlinear optimization problems. Okay, we just solve MILO, then we evaluate those constraints and add those gradient based inequalities. So all you need is a solver for MILOs and somehow the ability to evaluate gradients, okay, which is easy. Okay. So one limitation of this is that once you add this inequality, there is a chance that in the next iteration when you solve the MILO again, you might progress a little bit further towards the feasible region, and then you add another linearization, then you might progress further, then some more, and only in the limit you might be able to reach this particular feasible point. Okay. All right. So in this method, there is no guarantee that the number of inequalities that you have to add is finite. Okay. You might add many cuts which are close to each other. Okay, and in the limit you might be able to reach the desirable point. Okay, and remember that every time we add a few cuts, we have to solve a mixed integer linear program. Okay, which might progressively become more and more difficult to solve because I am adding more and more inequalities to it. Okay. So we need to somehow overcome this limitation. All right. So outer approximation does that by invoking a nonlinear optimization solver. Okay. So to make things faster and converging faster, we use this NLO technology, and this is where this previous lecture comes in very handy. So the idea is that instead of adding a linearization at this point, okay, so this was the point we got from MILO, I am not going to try to add a linearization here, but I am going to search for a point which is on the surface of the nonlinear region, okay, some place here. Okay, and try to add a cut which actually touches the region. Okay, and to get this point I will need to solve an NLO. Okay, I can't just do a small search around and get it. This point might be far away. Okay, all right. But at the same time, I need a guarantee that when I add this inequality, I should be able to cut off this point. Okay, it should not be just any other, you know. So, for example, suppose I add an inequality at this point. You know, this cut is not going to chop off this point. Okay, so I need to be smart enough to find a cut which is tight as well as cuts off the current point. Okay. So that is the main idea of solving this fixed NLP, where you take the original MINLO and fix all the integer variables to the same value that you got from the MILP. All right. And you get you know, a new point. So our earlier point was x star y star. I give it to an NLO solver and fix all the y variables to y star, solve the NLO and get this point x hat y star. Okay, so this point is x hat y star. Okay, and then add linearizations at this point. This linearization is guaranteed to be better than the ECP type of cuts. Okay, and also it is guaranteed to cut off x star y star. Okay, why is it guaranteed to cut off x star y star? We have fixed y star. We have found some other linearization at a point x hat y star, and I add this inequality. So the claim is that this inequality is going to cut off this x star y star. Why? Do we have a result like that?
Because X now satisfies linear non-linear constraints, so it has to be like in the
Yeah, but this point is also one of those, but it doesn't cut off, right? So why does this point cut off, not this? You know, so how did we get this point? We solved an NLO. So which result can we use to say that it is going to chop off this point? Yeah. So the result is actually there in front of you on the board. Yeah. So which lemma or which theorem shows us that it will be chopped off? Optimality result. Okay. So let's see, where is the optimality result? That side. Okay. So if I remove this little bit, okay, here, okay. So if you look at the optimality optimality lemma that we just discussed 30 minutes back, it guarantees that this linearization will cut off all points of this type. Okay. All right. Another advantage of solving a fixed NLO is that if we get a feasible solution when we solve that NLO, then it is also a feasible solution to my original model because it is satisfying all the nonlinear constraints because I just solved an NLO, and it also satisfies all the integer constraints because y star is fixed to some integer values. Okay. So then I get a feasible solution to the original model, and that, you know, gives me a good upper bound, okay, and helps in pruning a lot of search space. Okay. This solution that I may get as a bonus is not necessarily optimal, but still quite useful. All right. Any questions? Okay. So What about infeasible NLO? It is possible that when I fix y to y star and solve the NLO, I may get something infeasible. You know, it may say that there are no feasible nonlinear solutions.
In the landslide,
Huh. Huh.
that after solving this, we'll get the upper one.
This is a side bonus. This is not a requirement from the algorithm, but it is quite useful. Yeah.
So it will give the
Upper bound. Yes. Yes.
and our lower bound will be the which we have solved the MILO.
The lower bound progressively improves from the MILO side. Right. Any other questions? Okay, so if the fixed NLO is infeasible, so that means you know, I get a point x star y star, but there is nothing in the NLO region with that y star. The NLO will say that, you know, it is infeasible, but the feasibility lemma behind the screen tells us that it will give us a point, it will still give us a point x hat y star, okay, so some point here, okay, some point it will give at which you can still generate these linearizations, and it is going to chop off the current point and give us a guarantee that we will never visit y star again. Okay, so that is a pretty powerful result. Okay, that is the most important part of the, you know, whole theory behind this OA. Okay, so there is this idea that once you add these linearizations, you will not visit y star again in your algorithm again. Okay, and remember that y star is bounded, so there are only a finite number of y stars you can ever visit. Okay. So overall the algorithm looks like this. Okay, a 5-step algorithm: solve MILO, update the lower bound. If the MILO itself is infeasible, stop. If you get a solution, still stop. Otherwise, you know, you solve a fixed NLP at the MILO solution, and whatever point that NLP returns, whether it is feasible or infeasible, you add linearizations to your MILO model, and then again solve it, and keep doing this again and again until you converge. All right. So in every step, you know, in one round of this iteration, you will, you know, the first step tries to improve the lower bound by adding more and more cuts. If you are lucky, in step 4 you will sometimes hit a good upper bound, and that, you know, reduces the running time, and you keep doing this until the two values are close enough to each other, or MILO says that there is nothing else left to explore. Okay, so that is broadly your outer approximation algorithm. Okay, so we will stop here. I will talk about some practical implementation things about OA in the next session, along with you know, revisiting this proof of what it is doing exactly, and talk about that objective function f. You know, what do we do for that? Okay. All right. So let's take a break after the questions. Okay. So we get any point, suppose we get not just MILO optimal point, any point x star y star, okay. where this is integer, okay, and I'm going to solve an NLP or NLO and get a new point x hat y star. Okay, so the y star remains same because I have fixed it, and I have obtained this x hat. Okay, so what this result tells me is that once I add linearizations at this point, okay, the new system will not permit any feasible points, you know, so these are my new linear inequalities that I have added, okay, and they tell me that after this, you know, you will not get an objective function which is better than you know what is permitted by these again, and this is you know better than that, so it chops it off.
So you want to add linearizations Ly, not those.
Which
Saying that you want to add linearizations Ly.
these ones.
Yeah, the linearizations are both in terms of x and y, but if you choose y hat, then it tells you have to do what you did when you had x hat.
So here is another way of looking at it. You know, so forget all this. Suppose I go back to my original nonlinear world, where I just have a nonlinear optimization model, okay, and you know, and let us say this is my optimal point, x star, okay. If I add, you know, if I look at the linearizations here, okay, so I will get uh, a linear constraint like this and a linear constraint like this, okay. So, you know, assuming that this cartoon is true, and if I forget the nonlinear constraints now and only look at the linear constraints that I have generated, okay. Okay. So, so what you know, what we can see is that you know these linearizations chop off all points which you know which have a objective function value much lower than you know this one. Okay, so the optimal value, so whatever is the optimal objective value here is the optimal objective value here. Okay, so any points which have better objective value lower than that are chopped off by these constraints. Okay, so that is exactly what we are doing there. Okay, so we have a point which is outside the nonlinear region and possibly having much better objective value. So we add the linearizations at the KKT point of the fixed NLP and it chops that point off. Okay. All right. Okay, so we can take a break.